Welcome to day 3, section 1.3 notes. Today we're going to actually get into some fun trig things. So it's going to be a lot more of new information. We're going to be determining the 6 trig functions of angles of special right triangles and finding 6 trig functions of angles using the circular definitions and so on. So this part on the left here, that's what you did in geometry. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. That's SOHCAHTOA. Now we're going to start getting into the circular definitions. Okay, they're the exact same basic principle. All right, we're going to have to draw a triangle to see where we get these circular definitions from. So what's happening is this point XY, it's somehow going around in a circle that way. Okay, and as it changes, your radius stays the same. Your x and your y values are going to be changing, all right? So this is a ratio comparing those two things. Now, your reciprocal functions, these ones are going to be a little bit new, maybe. Cosecant, secant, and cotangent. They are just these up here flipped over. That's why they're called reciprocal functions. The part that's going to be tricky for people to remember is that cosecant goes with sine. Secant goes with cosine, and then cotangent goes with tangent. That one makes a little bit more sense. Okay, but they're going to be going together. So sine is y over r, cosine is x over r, tangent is y over x. So we're going to start off by finding the 6 trig functions for an angle theta in standard position at the point -2, 3 on the terminal side. So what we're going to do is we're going to start by sketching a picture. Okay, I know that -2, 3 is going to be over here somewhere. Let's say -2, 3. It's to the left and up. Our angle starts like this normally, right? That's how we have our angles. So technically what's happening is we're looking at theta going this way. So we're spinning it in a circle theta degrees. Now the way that we get our circular definition, it was sine of theta equals y over r. Okay, so I need to know what r is. So r is just the distance between the origin and that point. So it's the distance formula. So I've got -2 minus 0. For some reason I wrote comma 0. Squared plus 3 minus 0 squared. -2 minus 0 is -2. If I square that, I've got 4. And 3 minus 0 squared is going to give me 9. So r equals the square root of 13. So that tells me that sine of theta equals y value, which in this case was 3, over square root of 13. That's how to find sine, okay? Now, in most math classes, when we get a radical in the bottom, we have to rationalize. In trig, sometimes we have to, sometimes we don't. It kind of depends on the problem. So I'm just going to say, if you get a problem like this, you're done for simplifying, okay? If it was a square root of like 18 or something where you could simplify that, then you would do that, because square root of 18 is 3 squared root of 2. But square root of 13 can't be broken down. Don't bother rationalizing unless the directions say to rationalize, which you'd multiply top and bottom by square root of 13. Now, instead of just memorizing this, you can totally do that. You'll get the right answer every time. I like to kind of think of this in terms of a triangle that I actually can draw. So what I want to do is find that point on the terminal side and drop a perpendicular straight down to the x-axis. So over here, what I would have is this triangle right here. Okay, I basically have -2, 3 here, again with the comma 0. I don't understand why I keep doing that. And 0, 0 here, and this would be -2, 0. When we found the radius is square root of 13. Okay, now the theta that we're talking about here isn't inside this triangle. So we're going to use a reference angle, which again I talked about how you don't have to know this yet actually. I'm going to use a reference angle. I'm going to call it theta hat. Okay, and put a little arrow on top of theta. Just saying that if I had moved this into the first quadrant, this is the triangle that I would see. So like going back to this picture up here, okay, that triangle is inside quadrant 1. Since things are circular, with a circular definition, there's going to be a lot of duplicates. The only difference is going to be signs, all right? So I'm pretending that I have this triangle in the first quadrant, so I'm referencing what this theta would be. Now, if I wanted to, I could do my exact same sine, cosine, tangent definitions where I do SOHCAHTOA, all right? But I'm going to go back over here and do cosine of theta, which is x over r, which is negative 2 over square root of 13, which if I had this triangle here, which I didn't finish filling in the sides, that height was 3, and I'm just going to say that distance is negative 2. We can't technically have a negative distance, but think of the minus sign not as a negative, it's just a direction. I went left 2, okay? So if I did cosine, adjacent over hypotenuse, that's negative 2 over square root of 13, which is the exact same thing I have down here. Tangent of theta, that's a really bad theta. I'm going to redraw that one. Tangent of theta, that is just going to be y over x. Okay, y over x is 3 over negative 2. Opposite over adjacent is 3 over negative 2. They're the exact same thing. It's just another way of kind of writing it. Now, if I want to do the other one, so if I want to do the last three, the kind of new ones, cosecant of theta, I just take sine of theta and flip it over. This is one of the reasons why we don't always want to rationalize. It's because if I would rationalize that and then flipped it over, I would have had to re-rationalize and simplify and get down to square root of 13 over 3. Secant of theta, you flip over cosine. So that's square root of 13 over negative 2. And cotangent of theta is negative 2 over 3. Now, the way that I try to keep these ones straight, because they're confusing. I always want sine to be with secant because I start with the same letter. But that's not how it works. So I need to think about them as reciprocals because I'm flipping the fraction. And if I'm flipping the fraction, I'm going to say I'm also flipping that first letter. Okay, so I'm going from S to C and from C to S. Every time I flip the fraction, I flip that first letter. Okay, tangent and cotangent both have tangent in the name, so that one kind of, in my opinion, is a little bit easier to remember. Okay, so special right triangles. These are the ones that I've already kind of mentioned in the past, I think. We've definitely done them in geometry. I'm sure you've seen them many times. You have shorthands on the ways to remember them. So I always had my 30, 60, 90 triangle as a squared of 3, and 2a. Okay, or short leg, long leg, and hypotenuse. Right? The short leg, long leg, and hypotenuse all have their measurements based off this short leg. Okay? Like I know Miss Brantner in geometry taught the long leg is the short leg times square root of 3. The hypotenuse is the short leg times 2. Okay? I'm going to use the same letters for the 45, 45, 90. If you want to use different letters, you can. Each leg is a. The hypotenuse is a squared root of 2, and we get both of these from the Pythagorean theorem, or the distance formula. Okay, if you can remember these special right triangles, your life is going to be a lot easier. So, if we want to find the 6 trig functions of 30, 60, and 45 degrees, I'm going to draw a triangle. It's going to be a really bad one, but I'm going to draw it out anyway. So I've got a squared root of 3, 2a. So I'm just going to do all the 30s, and then I'll do all the 60s, and then I'll get to all the 45s. So sine of 30. Sine, so, S-O-H, opposite over hypotenuse. A over 2a. Well, I can simplify. A divided by a is 1, so I get 1/2. Cosine of 30 would have been a squared of 3 over 2a. The a's cancel out, so I've got square root of 3 over 2. And the tangent, opposite over adjacent, a over a squared of 3. The a's cancel. I've got 1 over the square root of 3. The next 3 for 30 are really, really simple. I take those first 3 and flip them over. Okay, cosecant of 30 degrees is 2 over 1, or 2. Secant of 30 degrees is 2 over square root of 3. And cotangent of 30, I flip over tangent, that is square root of 3. Okay, that's not too terribly difficult to flip those over. Now to do sine of 60, okay, I just go from that other angle. So I'm going to go across over hypotenuse, opposite over hypotenuse, And simplify, canceling out those a's, I've got square root of 3 over 2. Same thing with cosine of 60. I'll go adjacent over hypotenuse and simplify to get 1/2. If you notice, these ones are just switched. Tangent is also going to be pretty similar. I'm going to go across opposite before adjacent, simplify, and get, oops, sorry, started writing the wrong thing. I get square root of 3 because I'm looking at the reciprocal of it, essentially. Now, to flip these, I do the exact same thing that I had done before. 2 over square root of 3, 2 over 1, and then 1 over square root of 3. Now for the 45, 45, 90, okay, a square root of 2. This one should go a lot faster because cosine and sine are going to be the exact same thing, okay, because the opposite and the adjacent side are always the same. In this case, it's special right triangle. So when I simplify, I've got 1 over square root of 2. Because I would have a over a square root of 2. Same thing here. Tangent of 45 is 1. A divided by a. Okay, if I flip sine to get cosecant, that just becomes square root of 2. If I flip cosine to get secant, I get square root of 2. And if I flip tangent to get cotangent, I still get 1. The reciprocal of 1 is just 1. All right, so now we're going to start talking about the unit circle and quadrantal angles. Quadrantal angles is a weird word to say, but it literally has the word quadrant in it. It means the angles that are on the axes, okay? So, like both the x and the y axis, because our initial side is always the x-axis. If the terminal side is on the x-axis or the y-axis, it is a quadrantal angle, okay? We use the unit circle. Okay, anytime we have a unit measurement, we usually go with 1 because it's really, really easy, really nice. So we're going to say our unit circle, the radius is 1. If I'm looking at sine of 0 degrees, okay, if I'm looking at sine of 0 degrees, 0 degrees doesn't seem like it's going to be possible, does it? No, it doesn't. But we can have values for most of these, okay? If you look at them, they're all going to be zeros and ones. The only difference is we're going to have positive and negatives. All right? So sine of 0, if I try to draw a sine of 0, a 0 degree angle is just going to look like this radius. Okay? I'm going to draw this as a triangle, but know that that's not actually going to be possible because I'm going up 0. So that's a 0 height. Okay, if I'm looking at sine of this, I have to go 0 over hypotenuse, which is 1. So sine of 0 degrees is 0 over 1, which is 0. That's not possible. Okay, and we're talking about our radius being 1. So if I did cosine of 0 degrees, my adjacent is 1, my hypotenuse is 1, 1 over 1 is 1. All right? Now, I drew it as a triangle, a right triangle, but remember, this is 0, so it's basically just a ray on top of itself. If I'm looking at tangent of this angle, 0 over 1 is 0. If I'm looking at cosecant, okay, that's the reciprocal of sine. The reciprocal of 0 over 1 is 1 over 0. Can we have 1 over 0? No, that is undefined. Okay, that's not possible. You can't divide by 0. If I flip over cosine to get secant, if I flipped over 1, I get 1. And then same thing with cotangent. This one is going to be undefined. Okay, a cotangent of 0 degrees is going to be undefined because that's would end up being 1 over 0, which you cannot do. Now, if I do sine of 90, okay, I know in geometry we said don't do sine of 90 or don't do any of the things of 90. All that's going to be is, oops, I thought I was on the pen. Sorry about that. We've got this angle right there. If we look at these numbers, we used 1 and 0 for x and y. Same thing's going to happen here, right? So I'm going to erase that, and I'm going to rewrite our sine of theta is y over r, cosine of theta is x over r, and tangent of theta is y over x, our circular definition since we're talking the unit circle. Okay, it's the same idea as with that triangle, but it's going to be a little bit easier for some of us to understand. For myself personally, I like the triangle one. I think that's easier to understand, but I'm sure we've got people in both camps, so I'm going to show both. So again, sine of 0 was 0 over the radius 1. Okay, the y value was 0. So sine of 90, that's going to be straight up, right? So this is at the point 0, 1. So my y value is 1, my radius is 1, sine of 90 is 1. Cosine of 90, okay, my x is 0, my radius is still 1, so I've got 0 over 1, which is 0. And then tangent of 90 is y over x. 1 over 0 is not possible. Okay, you cannot divide by 0, so the tangent in this case is undefined. Now if I did cosecant of 90 degrees, that's flipping sine. The reciprocal of 1 is 1. If I flip cosine, the reciprocal of 0 is not 0, it is undefined. Now cotangent, we have to think a little bit because I can't just take undefined and take the reciprocal of it. There's not a reciprocal of a word. So I got to think about this piece over here. The reciprocal of tangent, so to get cotangent, would be x over y. X is 0, y is 1. So the cotangent of 90 degrees is 0. So down here, and I wrote it up at the top, our radius of a quadrantal angle is always going to be 1, because we're using the unit circle. The 1 makes our life a little bit easier. We don't have to mess with as obnoxious of numbers. All right, so for this example, we know sine of theta is negative 5 over 13, and theta lies in quadrant 3. Find the other 6 trig functions. It should say the other 5 because we've already got sine. But we're going to start off, draw a quick sketch. We know that we are in quadrant 3. So I know I've got this going this way. Quadrant 3 goes this way. Okay, my angle did this, but what I want to do is go from the end of this ray, technically not an end, but I'm going to drop a perpendicular down. Okay, so what I'm actually having is this right here where sine was negative 5 over 13. I'm going to redraw the triangle and give myself measurements. So this was 0, 0. Negative 5 over 13 is my sine. So I'm going to be looking at the angle by the origin. Okay? Theta hat. It's the one that is made with the x-axis and that ray. Okay, but I want to make it with the y-axis. The x-axis and the ray tells me that angle. So negative 5 over 13 for the sine. Now, negative is a direction, right? Technically, you can't have a negative distance, but we're using negative as the direction left or the direction down. So I can go left 5, I can go left 30, I can go down 15, whatever. But my sine, which is opposite over hypotenuse, right? Or if you remembered sine as y over r, tells me my y value is 5 and my r value is 13. One of those has to be negative in order to get a negative 5 over 13. I'm going to put it with the y value. The reason being is because radius is positive. We're using a reference angle, so we're kind of pretending that we move this thing back to the first quadrant. 13 didn't change. Now I need to figure out what my x value is. Okay? So I need to figure out what point basically that was at. So I'm going to put x here. So I've got x squared plus negative 5 squared equals 13 squared. And I'm just going to solve for x. When I subtract 125, I get 144. So x equals plus or minus square root of 144, which is plus or minus 12. Now, since I went to the left to get to quadrant 3, I'm going to say x equals negative 12. So if I've got x, I've got y, I can just kind of do the rest. So I'm going to say sine of theta is negative 5 over 13. We were given that one. Cosine of theta. Cosine is going to be x over r, so that's negative 12 over 13. Or if I had drawn the triangle here, negative 12 over 13. Tangent of theta is going to be a positive number, negative 5 divided by negative 12. That's just 5/12. Now to get cosecant, I'm going to flip over that fraction and get 13 over negative 5. I'm going to bring the negative to the top just because I like having the negative in the numerator instead. It's the exact same thing as 13 over negative 5. Secant, same thing. I'm going to put the negative in the top, but it's negative 13 over 12. And cotangent of theta is 12 over 5. Now, I forgot to put my thetas in here. That's a common mistake that I make and a lot of people make. So try to make sure that you're writing your thetas, because we're talking about sine, cosine, tangent of an angle, not just in general, of a specific angle. So I've got those 6 trig functions. So what did we cover today in this lesson? There is some new stuff and some complicated stuff. So this is going to be a good place to write your summary and to write questions about things you're not 100% clear on. Even if you're like 85% clear, jot a question down. I'll answer it when we come back to class in person. Then give a few of these homework problems a try. You do not have to do all of them. When you come back to in-person class, we'll have time to work and ask and answer questions. But I hope everyone has a great day, and I will see you in the future.